Hi, this is Dr. Jerry McNally with your Unit 1 review. If we go back and you remember that we have the structural and functional organization of an organism, we're going to start off with atoms and molecules. Those are considered to be the chemical level, which is the smallest level of organization. We then move up to cells. Cells are made up of a group of molecules. Again, molecules are made up of two or more atoms. Next is going to be a tissue. A tissue is going to be made up of a group of cells. If we take a group of cells that work together to perform a certain function, that's going to give us a tissue. So a tissue is a group of cells that work together to perform a certain function. Organs now is made up of a group of tissues that work together to perform a certain function. And a group of organs is called an organ system. And a group of organ systems is going to give us an organism. So to review, going backwards, an organism is made up of a group of organ systems. Organ systems are made up of groups of organs. Organs are made up of groups of different tissues. Tissues are made up of several cells. And cells are made up of molecules. And if we break the molecules down, we have atoms. Again, atoms and molecules fall under chemical organization. Then we have organ systems of the body. Don't forget the different functions of each of these systems. The integumentary system, of course, that is to protect. Protects the body. It makes vitamin D. It excretes. For example, it helps to cool the body if we perspire, and that perspiration then is able to evaporate. Also, we secrete oils in the form of sebum. Then we have the skeletal system. Skeletal system protects the body. It acts as levers for movement. It also helps to store minerals, such as calcium. And then next we have the muscular system. And the muscular system, of course, is for locomotion, for movement. Then we have the lymphatic system. Lymphatic system does a couple of things. One, it provides for the immune system. It also helps to regulate excess tissue fluids. If as fluids get pushed into the tissues, the excess can drain off into the lymphatics. Then we also have the respiratory system. Respiratory system is for the exchange of gas. Mainly we bring in oxygen and we breathe out carbon dioxide, which is a waste product from your cells. The digestive system is going to take large molecules. We're going to break those molecules down into smaller molecules, such as lipids, proteins, amino acids. So even the proteins are made up of amino acids, so we're going to break it down even farther. Those lipids, we're going to break those even farther down into fatty acids. So basically we're taking larger molecules, breaking them down into smaller molecules that could be used by the body for either energy or for building structures. Okay, terminology in the body plan. If you remember anatomical position, this lady here is in anatomical position where the body is erect, the face is forward, the feet are together, and the palms are facing forward. Some other different body positions. We have supine. If you remember, if you lay on your back, if you lay on your spine, you are supine. So basically supine is laying down face up. And if you're prone, you're laying face down. And my thought is if you're laying face down, then you're prone to somebody sneaking up on you. Okay, so prone is laying face down. and some directional terms you want to know. And again, these directional terms, excuse me, we have opposites that we have to consider. So you can't just say something is superior. You have to say it's superior to what. Okay, so if we look at some of those directional terms, we have superior versus inferior. Superior is up, inferior is down. Now we can also use another term for superior, and that's cephalic. Cephalic is toward the head. Or inferior, we can use the word caudal. Caudal is toward the tail. So cephalic and caudal are opposites, and superior and inferior are opposites. Then we have anterior versus posterior. Anterior is in the front. Posterior is in the back. And another term that we can use is ventral and dorsal. Ventral is in the front, and dorsal means, or ventral means belly, and then dorsal is in the back. Think about the dorsal fin on the back of a shark. And then we have medial versus lateral. Medial, if we look at this lady, you'll see that there's a white dotted line going down through the middle of her. Medial means toward that midline of the body, and lateral means away from the midline of the body. Proximal versus distal. Proximal is toward the body. Distal is away from the body. Now, we want to use proximal and distal when we're talking about extremities. So arms and legs. Think proximal and distal when you're thinking arms and legs. So for instance, the elbow is proximal to the wrist. And don't forget, this is all in anatomical position. So the elbow is proximal to the wrist because the elbow is closer to the body than the wrist. Now the wrist would be distal to the elbow because it's farther away from the body. Again, in anatomical position. Superficial versus deep. Superficial would be toward the surface. Deep would be, well, below the surface. So for instance, your skin is superficial to your bones. The bones of the hand are deep to the skin. Okay, body planes. This is how we would cut up a body. And this is important when you look at things like CT scans and MRI scans. So here is a sagittal section. Okay, now if we're very specific with this sagittal section, if you notice it's right in the middle of the body. So this is a mid-sagittal section. A mid-sagittal section will give you equal right and left halves. So remember, a sagittal section gives you right and left halves. If this were off to the side a bit, off of center, off of the midline, we would have what's called a parasagittal section, which would give us unequal right and left sections. And there we go, sagittal, mid-sagittal. We can also call it a median section. And again, parasagittal would be just off to the side. This one is going to be a transverse, horizontal, or cross section. A transverse section is going to give us a top and a bottom. Okay, so we'll have a superior piece and an inferior piece. In this one, this is a frontal or coronal section. That is going to give us a front and a back. And if we are off of the right angle, if we're anything other than a right angle, we're going to call that an oblique cut. And you can see this section here is an oblique cut. Now looking at body cavities, we have two main cavities, and that's going to be your ventral cavity and your dorsal cavity. Now what makes up your ventral cavity is going to be your thoracic cavity and your abdominopelvic cavity. And it's the diaphragm that separates the two cavities. And if we take the thoracic cavity and break that apart, we've got the pleural cavities where the lungs are found, and the mediastinal cavity, which is right in the center of the chest. Now, also some authors will throw in the pericardial cavity, which of course is where the heart lies. The abdominal pelvic cavity is divided up into the abdominal cavity and the pelvic cavity. If we draw a line from the top of the pubic bone to the top of the sacrum, that anything below that is going to be in the pelvic cavity. Now, if we look at the dorsal cavity, we're going to have the cranial cavity, which houses the brain, and the vertebral cavity, which houses the spinal cord. Homeostasis. Homeostasis is basically how we're going to regulate the internal environment of the body. Okay, the body tries to maintain itself. And basically, homeostasis is a value of variables that fluctuate around a set point to establish a normal range of values. So the set point is your ideal. We can usually go up a little bit above that value. We can usually go a little bit below that value, and we consider that a normal range. When you go outside that normal range, that's when you start to get into diseases and disorders. So again, the set point's the ideal normal value for a variable. And like for instance, if we look at the set point for body temperature, what is a normal body temperature? If you'd guessed 98.6 Fahrenheit or 37 degrees Celsius, then you'd be correct. Now, some people run a little bit below that. Okay, while the ideal set point is that 37 or 98.6, some people fall outside of that, still considered within a normal range, but it deviates a bit from the set point. Now, two things that control feedback, or that control homeostasis, is negative feedback. And if we have negative feedback, of course, we have positive feedback. Negative feedback, I want you to think of like a thermostat. On a thermostat, we set our temperature. Let's say we set it for 72 degrees. That's our set point. Now, it's going to fluctuate a little bit above and below that, but when it reaches a certain point, let's say we set it for 72 and the temperature drops to 68 degrees. Well, then that thermostat is going to send a signal to your heater, your furnace, and that furnace is going to come on and heat up the area until your thermometer in the thermostat registers the temperature around 72 degrees, maybe a little bit above, and then it sends a signal back to the furnace to tell it to shut off. That's where the negative feedback comes in, because once it gets the feedback that yes, we're at the correct temperature, then it sends that signal and says, okay, stop, keep going, negative, stop. We're at the temperature we need to be. So that's how it gets its name. And so if we look at this slide here, we'll see maybe going out of the normal ranges here. So an increase in the variable is detected by a receptor, and this is what you need as far as feedback systems. You need a receptor. That would be like the thermometer in our thermostat. And then number 4 here, a control center responds to information from the receptor. Okay, now again, if we look at our thermostat, it would be the thermostat itself would be the control center. Okay, so the receptor is the thermometer. The control center is going to be the thermostat itself. And then the activity of the effector changes, and so basically it's going to send a signal to the effector, and the effector in our thermometer or our thermostat example is going to be the heater, and so that affects a change. In other words, it starts blowing out heat into the vents. And then a decrease in the variable is caused by the response of the effector. Okay, so if we look at that in the body, a receptor would be like, well, we have, for instance, hot and cold receptors in our skin. Okay, the control center is going to be the brain, and the effector, if we're talking about temperature, might be our sweat glands, for instance. So, but we can also talk about like hormones and things like that. Most of those, not all, but most are controlled by negative feedback. So again, just to review, we have a receptor, we have a control center, and we have an effector. And this is what's going to help maintain homeostasis through negative or positive feedback. Positive feedback, now when a deviation occurs, the response is to make the deviation greater. And this leads away from homeostasis, and it can also result in death. Now, a couple of normal instances of positive feedback would be childbirth. Okay, you get a contraction, which leads to a stronger contraction, which leads to a stronger contraction, until finally the baby is born, the placenta is delivered, and that stretch on the uteral wall is no longer there, and the positive feedback stops. Also, blood clotting. For instance, if you cut yourself, platelets are going to stick to the edges of the tissues. They're going to give off chemicals that make other platelets in the area sticky. They'll stick to the platelets, which gives off a chemical that makes other platelets sticky, and so on and so forth, until the area is totally clotted up. This, however, can go out of control, and someone who is bleeding severely can actually use up all of their clotting factors, and if all your clotting factors are gone because you've used them up all of a sudden because of this positive feedback, then you're going to bleed out. Okay, diffusion through a plasma membrane, or actually movement through a plasma membrane. We have diffusion, osmosis, and active transport. Now, diffusion and osmosis are passive. That means there is no energy applied. There's no ATP needed. Batteries not included. Okay, this just it doesn't take anything for this to happen. We're going to talk about actually how each of these work in just a little bit, but again, no energy is required. Active transport, however, needs the input of energy. It needs ATP. So if we look at diffusion, diffusion is the movement of solutes from an area of high concentration to low concentration in a solution. So basically we need concentration or density gradients. We need to look at viscosity, which is how easily a fluid flows. And these things are going to regulate how fast diffusion can take place. Also, some other things that can affect diffusion is temperature. Increase the temperature, diffusion is going to happen a lot faster. Decrease the temperature, diffusion is going to happen a lot slower. So if you think about taking, say if we take a drop of ink and we put it into a beaker, you'll see a heavy concentration of that drop in one area. Over a little bit of time, you notice that that ink will disperse. Okay, so that's an example of diffusion. Now, it didn't take any energy. You didn't have to stick a spoon in there and start stirring. If you just left it alone, it would eventually disperse until it reached equilibrium and completely changed the color of that water. Now, I jumped ahead here to osmosis. Osmosis is the diffusion of water, water's a solvent, across the selectively permeable membrane or semi-permeable membrane from an area of low concentration of solute to an area of high concentration of solute. So you got to remember that. Now, my definition of a solute is a water magnet. Okay, a water magnet. And so just remember that. If you have more water magnets, water is going to flow to it. Okay, So, I mean, think about putting out a table, put a couple of magnets on one side of the table, whole pile of magnets on the other side of the table. We drop maybe a bunch of paper clips in the middle of the table. Which way is most of the paper clips going to go? Of course, it's going to go toward the area where there's more magnets. Okay? So think of solutes as a water magnet. Examples of solutes would be proteins, sugars, salts. All of those act in the body as a water magnet, as a solute. So again, diffusion of water, which is the solvent, across the selectively permeable membrane from an area of low concentration of solute, where there's fewer water magnets, to an area of high concentration of solute, where there's more water magnets. Okay? Now this is important because large volumes of changes are caused by water movement through a cell can disrupt normal cell function. Okay? So this is where we get into tonicity. We can have cell shrinkage or swelling. Isotonic situation is where we have the same amount of solutes in a cell as we have in the solution surrounding that cell. So again, let's use a beaker as an example. So if I have a beaker of water, and that beaker of water has 0.9% saline solution in it. So 0.9% sodium chloride is in that water. Well, that just happens to be the same amount of sodium chloride in the cell. So the amount of water going in the cell equals the amount of water leaving the cell, and the cell neither shrinks nor swells. So we call that an isotonic solution. Hypertonic solution, again, we're talking about the solution, not the cell. Hypertonic solution, let's say we dump a whole lot, maybe 1 or 2% of sodium chloride into that water. Now that's going to be a lot more salt than what's inside the cell. Remember, salt is a solute. It is a water magnet, which means it's going to draw the water out of the cell and cause that cell to shrink. We call that crenation. Okay, so cell shrinkage is crenation. But let's suppose we just take plain distilled water. Distilled water will have no solutes in it. We drop a cell in there, and what we will see is that cell is going to have more solutes inside the cell because the water, especially distilled water, has no solutes. So it is going to then pull the water inside that cell because there's more water magnets inside the cell. Pulls the water inside the cell, and the cell is going to swell up. And if we're using pure water, you can be sure that cell is most likely going to burst. And that is called lysis. Okay, you've heard of Lysol? It's called Lysol because when you spray it on bacteria, it disrupts its little cell membranes and cell walls and causes it to rupture. So lysis is cell rupturing or destruction. And this just shows an example of on side A here, on the beaker on the left, we have a certain amount of solutes. And if we look at side B, we have more solutes in that side of the beaker. So again, which way is water going to move? Well, there's more water magnets on the right, so the water is going to move from the left to the right. And if we look at the beaker on the right there, we'll see that the left side of the beaker, the water becomes more concentrated. On the right side of the beaker, that water becomes, or that solution becomes more dilute until they reach equilibrium. So if we measured the salinity of each side, side A and side B of the beaker on the right, we're going to find out that they have the same salinity. Okay. And again, just to recap on hypotonic solutions, isotonic solutions, and hypertonic solutions. Hypotonic solution with a low solute concentration results in swelling and lysis of a red blood cell if it's placed into that solution. So you can see that cell rupturing. In B, an isotonic solution with a concentration of solutes equal to that inside the cell results in normally shaped red blood cell. Water moves into and out of the cell in equilibrium, but there's no net water movement. Okay. And then a hypertonic solution, like we see in C here. Hypertonic solution with a high solute concentration causes shrinkage or crenation of the red blood cell as water moves out of the cell and into the hypertonic solution. Okay, tissues in histology. If we look at the tissue level of organization, we'll see that all the tissues in your body are made up of 4 different types of tissues. We have epithelial tissue, connective tissue, muscle tissue, and nervous tissue. So if we look at any type of tissue, it's going to fall under one of these 4 categories. Epithelial tissue covers surfaces because the cells are in contact with each other, so they make a nice covering. Okay? Think about your skin. The skin, what we see of the skin is going to be epithelial tissue. Skin is also made of connective tissue, and we'll talk about that in just a second. But back to epithelial, it's going to cover the surface pretty well. The cells are in contact with each other. Think about the tile on a floor. Those tiles butt right up against each other, and they form a nice surface, okay, to help protect what's below it. Epithelial tissue also lines hollow organs, cavities, and ducts. It also helps to form glands when the cells sink beneath the surface. Connective tissue, this is our biggest category. Okay, it varies so much. Bone, for instance, is an example of a connective tissue. But then we look at blood. Blood couldn't get any more different than bone, but yet blood is a connective tissue as well. So connective tissue, we have material found between the cells. So there's filler material. It's kind of like concrete. If you've ever seen a broken up piece of concrete, you're going to see that there's rocks and pieces of substances in that concrete. Think about those as the cells. Then you have the cement, which binds all of those things together. That's like our filler material, like our matrix is what we call it in the connective tissue. And connective tissues help to support and bind structures together. It stores energy, such as fat. Fat is a type of connective tissue. It provides immunity to disease. And again, I mentioned blood, right? In the blood, we have our white blood cells, and especially our B and T lymphocytes that provide immunity. It's found in the blood. It's a connective tissue. Muscle tissue. That's kind of a special tissue where the cells shorten in length to produce movement. And then nerve tissue. This again is another special tissue. And here the cells conduct electrical signals. Detects changes inside and outside the body. It responds with nerve impulses. The integumentary system, and basically this consists of the skin, the hair, the nails, and the glands. And it has quite a few functions. Protection is a biggie. Sensation. We have temperature regulation. If we get overheated, we're going to perspire. Also, the capillaries down in the dermis are going to dilate to bring more blood toward the surface of the skin so that we can dissipate excess heat. Vitamin D production. Okay, as skin is exposed to ultraviolet rays, it produces vitamin D. And then excretion. Like I said, we can excrete things like oils. We can secrete perspiration, sweat to help cool us. And sometimes we can even secrete or excrete waste products. Now, starting at the bottom and working our way up, the hypodermis, the skin rests on this, but it's not part of the skin. It consists of loose connective tissue. The types of cells we're going to find there are fibroblasts, which of course make fibers, adipose cells or adipocytes, and macrophages. Now we have another name for the hypodermis, and that would be the subcutaneous tissue, or in a clinical setting we would call it sub-Q. If you're an anatomist and you're dissecting a cadaver, we might call it the superficial fascia. Now looking at the skin, again going from the bottom up, we have the dermis. Dermis sits on top of the hypodermis. That gives us structural strength. It gives us cleavage lines. Again, if you remember, cleavage lines are kind of the direction that the elastic and collagen fibers are going in. And there's two layers. We have the papillary layer, which is the layer where you're going to find the dermal papilla. Now, if you notice on this picture, the dermal papilla, we have capillaries. We have some blood vessels there. Okay. And then, okay, that is the papillary layer. And then below that is going to be the reticular layer. So the bulk of the dermis is the reticular layer. And then if we look at the epidermis, remember, is avascular. Again, if you've ever done this as a kid where you take a straight pin and you put it just underneath the skin, underneath the epidermis, you know, you didn't bleed, did you? If you took that pin and you went past the epidermis into the dermis, you know, you get into that papillary layer there, now you can hit a blood vessel and you can bleed. But the epidermis itself, avascular, no blood supply. Gets its nutrients and everything by diffusion. It's made up primarily of cells, and the cells are going to be stratified squamous epithelium. And it's going to also have many layers to it too. Skin, if we're talking about thick skin, and that's going to be on the palms of the hands, the fingertips, and the soles of the feet, that is going to have 5 layers. If we're looking at the rest of the skin, there's going to be 4 layers of epidermis. Okay, so 5 layers of epidermis for palms, fingertips, soles of the feet, 4 layers of epidermis for the rest of the body. And again, that's just a recap. Thick skin has all 5 epithelial strata found in areas subjected to pressure or friction. Palms of the hands, fingertips, soles of the feet. Thin skin, more flexible than thick skin. And it does not contain the stratum lucidum. Remember, the lucidum is the clear layer. And this covers the rest of the body. And here's our layers. So if we look at this cartoon version here, we have the stratum corneum at the very top. It contains your dead keratinocytes. This is what sloughs off throughout the day. We have the stratum lucidum. Lucid means clear. It's the clear layer. Then we have the stratum granulosum, the grainy layer. Then below that, we have the spiny layer, the stratum spinosum. And then below that, we have the stratum basale, or germinativum. The older name germinativum refers to the fact that this is where mitosis is taking place. These are germinative cells. Again, if you think about planting a seed, plant a seed, you water it, what do you hope that seed does? Germinates. What that means is the cells are dividing and splitting, and that's exactly what's happening in this basal layer, or this germinative layer here. That's the epidermis. Now, if we go below that, we're into the papillary layer of the dermis. And again, this is where the blood vessels are. Okay. Now, again, how do we remember this? Here's our mnemonic. Don't forget, crying little girls spray germs if we're talking about germinativum. Or crying little girls spray boogers if we're looking at basal. So here's a crying little girl spraying boogers all over the place. Okay. Now, let's suppose we're walking along and we don't see this nail and we happen to step on it. Ow, that looks painful. So again, let's shove that nail through the epidermis down into the papillary layer of the dermis. And so the layers that nail is going to go through are, we start off with the stratum corneum, then we go into the stratum lucidum, then the granulosum, then the stratum spinosum, then the stratum basale, and then all the way down into the papillary layer of the dermis. So in that case, if we pulled that nail out, we would definitely be bleeding.